In this video, we're going to talk about the motional electromotive force. So we can derive an equation for the motional electromotive force using a very simple um, illustration right here. So suppose that we have a conductor. So this is a conductor that has a length L. Now there is electrons in this conductor, and we place it in the presence of a magnetic field that is pointing into the paper. Now, if this conductor is moving with some velocity v in the presence of this magnetic field, then using the right-hand rule or using vector products, I can calculate the magnetic force. So again, if this conductor is moving to the right, so this is in the x direction here, and I have a magnetic field that is pointing into the paper, then I can calculate the force on the electrons that are inside the conductor. Now, because the electron is a negative charge, so when I calculate the magnetic force on the electron, you're going to notice that the magnetic force is going to be pointing down. Now, the magnetic force is going to push electrons to the lower side of the wire, and that would leave me with an excess positive charge on the top side of the wire. So the presence of the positive charge at the top and the negative charges at the bottom is going to generate an electric field that is going to push the electrons up back. So we can say that when the system is going to be at equilibrium, then it means that the electric force must balance the magnetic force. And when I solve this equation, I just get E is equals to V times B. Then I can calculate what the voltage between, so if I know what my electric field is, I can calculate the voltage between these 2 points by multiplying the electric field by the length, which is given by this quantity right here. So this is an example. So this is called the motional EMF. So this is just one way to derive this equation. Now there is a second way. There is a second way that we can derive the motional EMF. So if we look at this picture right here, so suppose that we have a coil that has a length L. Now we're going to place this coil in the presence of some magnetic field that is pointing into the paper. But notice that so this coil, so the wire at the top is fixed, it's not moving. The wire on the left side is also fixed. The wire at the bottom is fixed. But the wire at the right here, the golden wire, is movable. Now, so suppose that we give this some initial velocity v, so that this is moving to the right. So notice that as this is moving to the right, this area is changing. So when I calculate the flux, the magnetic flux is just going to be the B times the area. So the area is just equal to the length times X. So it means that my magnetic flux is equal to B times L times X. Now, when I calculate my induced EMF, which is equal to negative the derivative of the magnetic flux with respect to time, notice that this is just given by negative BL times dx by dt. And so because dx by dt is just the velocity, then I can calculate my induced EMF using this equation right here. So this is a second way to derive the motional electromotive force. So for the most part, you don't need to really worry about the derivation of this equation, but you need to understand exactly how to use these equations to solve problems. So we can represent the motional EMF can be represented by this equivalent circuit right here. So you have the induced current. So you have so when this cable here is moving to the right in the presence of this magnetic field, because the motion of this cable is going to cause the area to change. So in this case, notice that the magnetic field itself is not changing, but it's the area of the loop that is changing. So the changing area is what is going to generate this electromotive force. Now, in this particular example right here, we're going to notice, and we'll talk about this a little bit later, that the current, so the induced current, is going to be pointing in the counterclockwise direction like this. So if the induced current is pointing in the counterclockwise direction, then it tells me that the voltage, so the induced voltage, is induced in such a way that this will be the positive and this will be the negative. So this will be the positive end here, and this will be the negative end, so that the current is going to flow in this direction like that. Now again, I mentioned that we're still going to talk a little bit about about how to derive the direction of the current. So we'll talk about that later. Now the resistance here is the total resistance of the loop. So it's the total resistance of the loop. So if you know what the total resistance of the loop is, and if you know what the induced EMF is, you can use Ohm's law to calculate the magnitude of the induced current. So again, for example, the magnitude of the induced current is just given by the electromotive force divided by the resistance, which is given by this equation right here. All right, now let's look at example number 30.2. So in example number 30.2, we're going to look at the magnetic force acting on a sliding bar. So the picture here illustrates what we're going to be looking at. So we have a conducting bar that is illustrated in this picture, and is placed in the presence of a uniform magnetic field that is directed into the page. It tells us that the bar has a mass of m, its length is L, and the bar is given some initial velocity vi to the right, and is released at t equals to 0. So using Newton's law, find the speed of the bar as a function of time after it is released. So what we're trying to do here is that, so we know that in the presence of a magnetic field, there is going to be some magnetic force that is acting on this bar right here. Now, the magnetic force is going to be pointing to the left. Now, because the magnetic force is pointing to the left, you're going to notice that as this, so the velocity vector is going to reduce in magnitude, because the magnetic force is acting in the opposite direction. So we can set up the system like this. So again, so Newton's law tells me that the sum of all the forces acting on the system is just equals to the mass times the acceleration. Now the magnetic force on this wire right here is given by negative I times L times B, where I is just the current in the wire, L is the length, and B is the strength of the magnetic field. So again, if you remember this, so this expression comes from chapter number 29. So we said that a conductor carrying a current placed in a magnetic field would experience a force that can be given in this by this quantity right here. So if I set this to be equals to m times the dv by dt, then I can write this equation as m dv by dt is equals to, so in place of the current, I substitute all of these. So I end up getting negative b squared L squared over r times v. Then using calculus, I can write this as dv over v is equals to all of these times dt. Then if I just do my integrals, so I want to integrate from some v initial to some v final, and then you end up with this equation right here, and then with a little bit of mathematics, you can show that the velocity is going to be given by this equation right here. So what this tells me is that when some initial velocity is given to this sliding bar at t equals to 0, then the magnetic force is going to slow it down such that the velocity is going to die off exponentially. It's going to decay exponentially. And it's given by this equation right here. So V is equals to V initial e to the negative t over tau, where tau is just given by this quantity here. All right. Now let's also look at example number 30.3. So this is an example of a motional EMF induced in a rotating bar. Now we have a conducting bar of length L that rotates with a constant angular speed V about a pivot at one end. A uniform magnetic field B is directed perpendicular to the plane of the rotation as shown in the figure. Find the motional EMF induced between the ends of the bar. So this is the setup of my system here. This is my pivot point. You have a magnetic field that is going into the paper. The length of the rod is L, and so what we're going to do is I want to calculate the motional EMF induced between the ends of the bar. So I can say that so based on the equation that we've already derived before, I can say that the EMF that is induced, so using calculus, I can use a small area here, call it a small length, dr. So I can say that the EMF induced by this element here, dr, is just given by BV times dr. Now because this is so I can calculate the total EMF by doing an integral over dr to get my total EMF. Now I know that V, so because this is moving in a circular motion, I know that V is just given by R times omega, where omega is the angular velocity of the rotation. So by substituting V equals to R times omega, I can pull omega out of the integral, assuming that omega is constant. And then when you run this integral from 0 to L, you get the total EMF as 1/2 times B times omega times L squared. All right, so now we're going to talk about Lenz law. So Lenz law explains the reason why there is a negative sign in this equation right here. So we can state Lenz law by saying that the induced current in the loop is in the direction that creates a magnetic field that opposes the change in the magnetic flux through the area enclosed by the loop. So the induced EMF is always going to be created in such a way that the direction of the current would be opposite to the direction of the force that induces the current. So we're going to look at some examples here to really help us to understand. Now let's look at this example right here. Now suppose you have so this is an example of the motional EMF. So you can see that because the magnetic field is pointing into the paper, then the induced current has to be created in the counterclockwise direction. Now, if the induced current is pointing in the counterclockwise direction, then you can see that using the right-hand rule, the magnetic field produced by the induced current is going to be pointing out of the paper. So Lenz law simply tells me that the EMF is induced in such a way that the current is going to flow in a direction such that the magnetic field generated by the current is going to oppose the original magnetic field creating the current. So in this example, since the current is pointing into the paper, since the magnetic field is pointing into the paper, the current is induced in the counterclockwise direction, such that if I were to calculate the magnetic field generated by the induced current, then the magnetic field generated by the induced current will be pointing out of the paper.